for the course. So I have all my lectures as planned. We have our class Monday and Tuesday, and then I start with the topic on process and stability, giving introduction and then some definitions. Then moving on to the next on the topics related to oscillations and the mode analysis. In this part of the course, I have few hours left planned for the practice, which I will discuss. So I have some exercises designed for you, and you have to work on that. So it will be like, because the course is about dynamic. So that means we have to focus on the power system components or power system network, how to model it, and how to perform analysis, dynamic analysis. So in that respect, some of the exercises have been planned here in the course. Then I also have some discussion on advanced topics. This is all related to phasors and the worms. In fact, let me be very clear, this course is a very conventional course about the power system, but here we discuss about the conventional power system components, and a conventional way about the power system dynamics, and then how we apply the control. So that means we have a large network, a large power grid network, how to perform the modeling, how to develop the model, how to perform the analysis, dynamic behavior, and then again some control. So in the course, in respect to the control, I have included the frequency control and voltage control. But again, it is all as a part of the conventional techniques, conventional approach being applied in the power network. But I have also, as I said, I have some advanced topics, because we now the conventional power grid, it has moved forward and it has advanced level of operation being adopted in the system. So in that case, we have the use of phasors and as a worms. So I will discuss that part. Then in respect to the dynamic analysis, I will consider a small network as SMIB, small single machine infinite bus system with the automatic voltage regulator. And then some discussion about the exercises or the examples which is given in the Kundur book. Then we move to the another topic on with the inclusion of Boston stabilizer, and then how to develop the excitation systems and perform study. Then next topic I consider I have on frequency control. So again, there we have different parts actually. So one is the how to model it, then primary speed control, and then characteristics, regulation part, supplementary control, and so on. Next, we move on to the topic on voltage control here, or the reactive power control in a network. And then some topics related to modeling of power network with renewable resources integrated. So now, with this respect, I have the project group. So in this case, you have to decide yourself to work in a project as a group. So you can have 2 students or 3 students in a group, and then you can work on stability analysis of a power network, bus network, renewable integration. So I will share with you the MATLAB toolbox, and then here we will have some problem definition. What exact problem you have to work on, what analysis you have to exactly work on. So with this toolbox, which will be provided to you, you have to perform some kind of analysis here on the system. And then another topic which I have included is the power quality, and then islanding here, because when you talk about the DG system, so we have the issues related to islanding detection and as well as the power quality signals. If you remember last semester, we discussed some of the norms, some of the standards that we have for power quality definitions. But this semester we have some topics on power quality, and here we will discuss about what are the different techniques. And for teaching these topics, I will use some of my own research work with the use of signal processing techniques. How these signal process techniques have been useful in analyzing the power quality, and that is for detection and even classification. With this, now we have the latest version of the MATLAB. They have the wavelet toolbox available, and I will provide you the power quality data signals, and we can download it from IEEE standardization website actually. So I will provide you the different power quality signals which are available in their IEEE standard repository website, and you will use the wavelet toolbox and to analyze the power quality signals here. So these are the two projects which we have planned for the course. And then again, some exercises as this referred here in the lecture plan. So altogether, you will be required to submit these exercises, and then again work on the project which you have. This will be your choice whether you want to work on this problem or you want to work on this problem. So these two are will be mandatory for the submission, and you have to get it approved.
So do we have to do both the projects, or you can select one of them?
One of them.
Okay.
It will be one of them. So I think for this course, as I know, we have 5 students registered for the course. So you can decide in your group what will be group 1 and group 2, and then on which problem you want to work on.
Okay.
And then in this case, for the project group, I wish that we will discuss more in detail when we have progress to the lectures. We will, in fact, you have to have some results obtained, and then you have to give a presentation. Each student will have an allotted time of 10 to 15 minutes, and then present what was the role or the responsibility in the work as given in the project. So they will present
are the projects a part of the grade? Are they graded as part of the final exam?
No, I think grading is only for the last end semester examination, but this is to be approved for this. That's what I could see from the description, because I have not modified anything. So
okay,
as such, but it has to.
So these are mandatory assignments, but they are not graded.
Mandatory, yeah.
Okay.
For the approval, and then but your grading will be based on your end semester examination. But of course, you have last semester also you had the course with me. So if you remember, there would be some questions in the end semester examination from your group from this project work as well. So that could be always there as a part of a evaluation, you can say.
Yeah, I understand that. That's good.
Okay. So this is what we had, and then lastly, I can say that Although you have several books on power system, dynamic analysis, stability and control, but I must say, in fact, the book by Prabha Kundur, this is very good book. In fact, it was written long back, 3 decades back, but it's a very good book. And in fact, if you when you read the book, the notations for the variables, the way they are discussed, the parameters of those variables, they are very clearly defined. And then they have several examples, solve examples to explain you about the performance analysis of the topic which are discussed in the book actually. So I can advise that this is the, in fact, I have also read another book by PM Anderson. So that is also quite good book. I have not listed here, but Anderson, I get sometimes confused with the notations actually. But with the Kundur book, the notations are very clear, and thus I always advise my students who are at advanced power system level of courses, so to refer this book actually. Then there is another book by Hari Sadat here. They have they start with the topics from a very brief, from a very basic one, and then they have some solve examples using the MATLAB. And that could be one way of learning about the system analysis or the performance analysis. And they have given some useful examples with the use of MATLAB for analysis of the power system. And that's why I have included this book as well here. In most of the lectures, PPTs which I have it used for my lecture, they will have the name of the books and the pages referred at the bottom. And then, as I said, for the exercises, relevant papers and the MATLAB files will be provided to you here. Right. So, if you have any questions, we can have now. No? Yeah. Okay. So then we move to the, and you can see that this is the canvas for the course, and I have, as of now, I have uploaded the schedule, and then the different lecture slides I have uploaded here. You can see. In fact, I have, as per the, what are the main topics? Let's say, because this is about the dynamics introduction part. This one is about the excitation system. So this is the lecture slides. Then related on topics on active power frequency control. Then again, they are in different parts actually. So I have them here. Then reactive power voltage control, then DG modeling, stability and control, this one, and the last one, power quality and islanding. I have not yet uploaded some extra files for your understanding related to the topics, but it all depends on how we progress, and then if there is any need, so I will upload some of them as well here. Right? Is it okay?
Yeah, it looks good.
Fine. So next, I have this lecture is on the topic power system stability and monitoring. And but may I know what is the background? Have you studied the power system analysis or the power system dynamic course in the undergraduate level in the previous semesters?
No.
Maybe even at undergraduate level, it could be.
Undergraduate, we have studied like very, very basic power system, like 2-bus or 3-bus system, and how to find the PQ and using, Newton-Raphson or Gauss-Seidel, like very basic stuff, not really a dynamic analysis.
But about the stability, you have not covered.
No.
Okay. How about others? Claire, Andres, Osake, how about you?
Oh, sorry, I didn't get your question, sir.
What I mean to say, I just wanted to know the background. Do you have topics or any course already covered at undergraduate level, which has discussed about the stability, partial stability, or the dynamics in the previous courses which you have attended at undergraduate level?
Yeah, certainly there will be, but it's just that it's a pretty long years back. So one needs to refresh the memory.
Okay, you have to refresh. Okay. Claire, Andres, how about you?
Yeah, I had something about it,
Okay.
but not so much.
Okay. And then Claire. Is that, yeah. Okay. Anyway, in fact, I can share with you this one. In fact, I hope you are aware that I have this YouTube actually on the YouTube. Some lectures are already uploaded actually, right? And in fact, if you want to have the basics about the power system stability, so this is the lecture which I have it. It is actually as there are these are in 5 parts actually, as day 1, and then you have day 2, day 3, day 4, and day 5. All these lectures day wise, they are all referred to the power system stability. And I start with what is stability, what is the definition, and then I give some introduction about, because the stability, it refers to the generator dynamics, synchronous generator dynamics. So here I have some illustration about the generator angles here. And then how you analyze the stability. So thus we have the equilibrium criteria approach here. So all these are discussed in the lecture, which is on day 3, day 4, and day 5. Because based on this equilibrium criteria, we can say whether the system will remain stable or become unstable whenever you have some disturbance. So I would suggest that you should go through these lectures, videos, I mean, which is mainly discussed on stability. And again, this discussion on these topics, they are all at a very basic level. I have not discussed the advanced level of stability here. But what I will refer in our course, it will be a little bit advanced. So it will be always helpful, I think, if you go to these video lectures, which are already available on YouTube. Then apart from this, on stability, maybe later on I will discuss a little bit more. I have a few more lectures. Those are advanced topics actually. So this is a small signal stability analysis in the part-wise, part 1, part 2, and part 3 here. So now the discussion that I have here in these lectures, they could be useful for the topics which I cover in the course here in this semester. Then again, there are some more lectures here, power oscillations, and then about the active power control and this one. So all these lectures which we have, they could be useful if you go through them and then having a good understanding for the topics which I will cover in this course here, right? So will it be possible to have a search on this YouTube?
Yeah, could you add the link on Canvas?
Yeah, I will add it. And then if you want, we just type this one. This word. You just type this one, and if you do this way, you get this link. And from here, you have all those, in fact, videos available with you. So, in fact, I advise all my students here in India when I used to teach. So in fact, these lectures last year, actually during the COVID, I prepared, I recorded them and then uploaded it on the YouTube actually. So I advise my students to whom I teach power system. So I tell them that, okay, you can refer some of these video lectures here. Then, okay, we move to this one. So, right. So this is the first lecture that we have, and then with this, these are some of the goals which we have to set for your learning. When you go through these topics, you should be able to define stability, understand the oscillations, power system oscillations, and also able to some way of analysis, mainly to the small signal, linearized model. So how you are able to analyze the small signal behavior for the system dynamics, and that will be for low frequency power oscillations here. And then I will discuss the use of the PMOs here, phasor measurement units, for wide area network monitoring. So in fact, how should I have it? No. Okay. So here, how this topic is important, we must understand that we have several generators in operation, and these generators, they are interconnected through the lines, and then we have them power being fed to the load. And in most of the cases, you have the several generators in one power plant and then connected to the load through a long network. It could be transmission network and then sub-transmission and distribution network and so on. So you have the load at far away distance, geographically distance. Now, when we have several generators, it is very important that these generators, they operate in synchronism. So we say that these generators, they have to be kept in synchronism operation. So that means the relative motion could change here, and that could be too much, and you may observe some way of uncontrollable oscillations, and that may lead to damage the generators as well as the equipment here. So if in case you are not able to maintain the synchronism between the generators, and that could occur because of some disturbances, and because of some disturbance, the relative motion between the generators can change. You may have oscillations. We will discuss about this, what we refer here oscillations. And because of these oscillations, there could be a damage to the generators. Mainly, here we say the damage to the generators, it will be as a part of damage to the shaft of the generators, mainly for those generators which are in the thermal power plant, because in thermal power plant you have long shaft of the generators, and in some cases the length of the shaft of the generator could be 20 meter or 30 meter as well. So if in case you observe some way of undesirable behavior in the form of oscillations, which we observe on the shaft, so it may damage the generator or even other equipments. Normally, against this consequence, against this damage, we have the use of relays, and these relays can detect such condition, and they can trip the generator before the damage occurs. But if the relay detects this condition of oscillations and the trip of the generator takes place, it means you have an outage of generator. So that means the shutdown of generator. And if I say, for example, 500 MVA generator or 600, 800 MVA generator, large size of the generator, and because of such consequence, some undesirable behavior in the system dynamics being observed, and the relay causing a trip of such generators. So that means the 500 MVA, 600 MVA power is suddenly cut out from the system. So that is again undesirable, because we don't want the generator outage, because we always want our power demand to be met by the generators. And if by any of the reason you are not able to meet your demand, then definitely the mismatch between the generation and demand will take place, and then again the problem will arise about maintaining the synchronism between the generators here. As I said, normally the tripping of the generators, they can prevent the damage, but because if there is a tripping of the generator, that means outage of the generator, and suddenly if you have an outage of the generator, right, so you are not able to meet your demand from the load side. So that means there is a mismatch between the generation and the load, and that may result into under frequency, because power generation is low, your load demand is more, and in that case the system frequency will dip here. Can you hear me? Yeah.
Yes, it
Yes.
was frozen for a second, but now it's back.
Yeah. Okay. So it is very much obvious that if you are not able to maintain the balance between the generation and the demand, the under frequency will be observed in the signal. You can say that if this scenario is observed, if let's say you have a generator outage, you are not able to meet your demand, then you can say that okay, and you want the match between the generation and demand, so you can argue that why not we interrupt the load. So that means you disconnect the load. So that we call it as load shedding. So that is possible, but again, this is perhaps not desirable. That the power has to be met actually by the consumers, and in many cases, I think you know that if there is a load shedding or the power disruption to the consumers, and in that case, some of the companies, they have to pay penalty. So again, the switch problem arises if you have the load setting. So this is again undesirable. Now, but if you have under frequency and this is allowed to take place, let's say the worst case, then this may result into cascading outages. Let's say one generator outage. You don't have the demand being met with the available generation, then what will happen? The under frequency takes place. And let's say because of the under frequency, because of the dip in the system frequency from the nominal value from 50 hertz, let's say, right? And let's say the frequency dips beyond a certain range here, let's say beyond 1% or the 2%, then again we have the use of relay. And if the relay has a detection of under frequency occurrence, then again that relay will trip some more generators. So that means the tripping of some more generators can take place. That means you can have one by one outage of generators, right? And that we call it as a cascading outage of generators. And if you have cascaded outage of the generators, and this takes place in the complete region, in the complete area, then finally it may result into the blackout. So that means the complete blackout means full shutdown in your complete network. So that is the consequence which we may observe if in case you are not able to maintain your generator in synchronism and you allow the under frequency to take place here. So that's the stability here, it becomes an importance for us. Right? Is it okay?
Yeah.
Yeah, fine. So here I have some of the common terms actually, which I think you should be get familiar when we are discussing about the power system. The first one refers to the quantity. What is operating quantities? Mainly it will refer to the variables, system variables. So it could be electrical variables or it could be physical variables here. And these variables, they are either measured through some sensors or it may be calculated, estimated. And these variables, it could be because electrical variables, like let's say it is like voltage, current, power, active power, reactive power, and physical variables, it could be like because frequency is a electrical signal, you can say, but when you talk about the speed will be as a physical variable. So these variables, they describe the operating condition of a power network. So if I say the frequency variable, frequency is 50 hertz. If I say the system bus voltage, let's say you have a bus network of 400 kV, and if you are able to maintain, if you are able to maintain a bus voltage of 400 kV, so it means that the system is very much stable actually, is it? Okay. Then, as I said, these quantities, they include real power, reactive power, apparent power, and then the phasor quantities of the voltage and the current here, right? I'm connected, I hope, right?
Yes.
Okay. And then another one common term which we normally use is the steady state operating point or the steady state operating condition. So when we say the word steady state, that means it will be a condition for a power system, a condition for a operating condition for a power system for which the operating variables like voltage, current, the power, generator power, or the power generation, load demand, everything, voltage, bus voltage, everything. So it refers to the operating condition of the power system for which the system variables, these variables, which characterize the system behavior, they are constant. So that means this quantity, the operating quantity, the operating variables, they are more or less constant around the operating point. So if I say, for example, you have power generation something 500 MVA in the complete network, and your load demand is also something of about 498 something or maybe 510 something. So there is some mismatch here, right, between the generation and the demand. But if I say exact demands, 500 MVA demand and 500 MVA generation, in that case, you will observe that the system frequency will be exactly 50 hertz, right? And then again, the bus voltage, let's say the bus voltage in the network, it is 132 kV, and then you will find that, let's say you have some 4 bus network or 10 bus network, right? So all these 10 buses, they will have exactly 132 kV maintained. So that means the operating variables, frequency, the voltage, the bus voltage, they are exactly constant. And for that operating condition, we say it as steady state operating condition. That means the system is not perturbed. The system is not under any influence of disturbance. That means generation is constant. Generation will be constant because your load is constant, right? So if your load is constant, you have regulated your output power from the generator to match with the load, so the generation is constant. So if you have perfect match between the generation and the demand, then the system variables, operating variables, will be at steady state condition, and thus there will be no system dynamics behavior. The system is steady state here, right? Now, another point term which we use here is the synchronous operation of generator. So we have generator which will be in synchronous operation with the network. So we normally say synchronous operation of a generator means one generator, it is in synchronism with the network, with a large network. So that means you have 500 MVA generator or 800 MVA generator or even 1000 generator, large generator, which is in synchronism with a large power network. This is one way of saying. Or it could be also saying that, let's say you have some generators in the power plant and then connected through a line to another sets of the generator in the power plant, which are let's say located at a distance of 50 kilometer, 100 kilometer. Then we say that, okay, the generators, all the generators in these two power plants, they are in synchronism to each other. So normally we use the word synchronous operation of a generator. It is with respect to, so that remember one thing, we always say the word synchronism or synchronous operation of a generator. It will be with respect to a network, or it will be with respect to another sets of generator. The word synchronous operation or the word synchronism, it is never talked about as a single quantity. I mean, as a that means we will never say that this generator is in synchronism. We will say that this generator is in synchronism with respect to other generators or other or the complete network. It will be. That means the word synchronism operation or the synchronous operation, it is always a relative term. It is always a relative term. Remember one thing in the previous slide, when if we refer, we have said the generators must be in synchronism. Here we have said the word relative motion. So that means relative motion between one generator and the complete network. That could be relative motion, or it could be the relative motion between the sets of the generator in one power plant against the sets of the generator in another power plant. So it will be always a relative motion. Synchronism will be always a relative term here, right? Is it okay? So now, if in case if the average electrical speed or the frequency equals the angular frequency of the network or the electrical speed of the other machines here. This is another way of how we say the synchronous operation of a generator. How we say that the generators are in synchronism. How we say that? It will be if the average speed or the frequency of a generators that equals the angular frequency of the network. So that because we are saying synchronism operation of generator with respect to the network. So if the speed of the generator equals the angular frequency of the AC network, or it could be the electrical speed of other generators. So because synchronism is also with respect to other generator. So we always say synchronism operation if the frequency of the generator equals to the system frequency or the frequency of other generators in the system. Yeah. Right? Is it okay? Right?
Yes.
Okay, we move to the next one. Then I have a few more. So here we have the definition, how we define the stability. This definition, which I have referred from this paper actually, long back published. So it is actually this is again a standard definition. It says that it is the ability. It is the ability of electrical power network which is at initial operating condition. So let's say that you have your power network which is initially operating at steady state condition. Here we have set steady state operating condition, right? So let's say that your power network is at steady state operating condition. The system is not perturbed, there is no disturbance, and your system is in steady state, generation, load, everything is steady state. And thus the operating conditions, the operating variables are constant, they are not varying, right? There is no deviation in the frequency, there is no deviation in the system bus voltage. So thus the system is at steady state. So if in case, so it refers to the ability of your power network which is initially at a given operating condition, and you can say that it is at a steady state, right? So it is the ability of electrical power system which is at a given operating initial operating condition to regain, to change, that means to regain a new state of equilibrium, to achieve a new state of equilibrium after being subjected to some disturbances. So that means let's say that your initial condition was steady state, but following the disturbance, following the physical disturbance, let's say your power system is intact, you have generators, you have transmission lines, you have the load, right? And if I say that the system is perturbed, that means there is some physical disturbance being applied. It could be in the form of a load. Let's say the load has changed. Load could increase, load could decrease, right? There is some disturbance in the form. So yeah, sorry for that. Okay. So yeah, we were discussing about the system stability. So it is actually the ability of an electrical power network which is operating at a given initial condition to regain a new state of equilibrium following the disturbance. So your system was initially, let's say, at a steady state, and after being subjected to some load disturbance, or it could be like, let's say the line has tripped, right? Let's say the line has tripped, or maybe you can have an example saying that the generator has outage. The generator has shut down suddenly because of some malfunctioning. So these are actually the physical disturbances. So if in case your electrical power network, which was initially at a steady state, or it could be any operating condition, and if it is able to achieve, if it is able to achieve a new state of equilibrium following the disturbance and with system variables being integrity preserved. So if the system variable, let's say the deviation in the voltage, deviation in the frequency, right? They are within the limits, right? Because if there is a mismatch between the generation and the load, frequency will deviate, your bus voltage will deviate. And if these variables, they are within the limits, acceptable limits, then we say the system integrity is preserved. So that means ability of the power system to achieve a new state of equilibrium, right? And we say the word integrity of the system being preserved. That means the power system remains intact without tripping of generator or load. So that means you don't trip any generator, you don't trip any load. Whatever the generators you had, whatever the loads you had, if let's say the load has increased, right, then you should be able to increase your generation that we require, right? So, but if I say the load has reduced, then you should be able to regulate your generator so as to reduce the output power from the generator, right? So we don't want any undue, we don't want undesired tripping of generator or the load. And if this you are able to achieve, then the system integrity will preserve, your power network remains intact, and it will achieve a new state of equilibrium, and the system will be stable. So that means stability will be actually a condition of equilibrium between the forces, between the opposing forces. Now just see here, your electromagnetic torque, right, from the generator side, and your electrical torque from the load side, right? It is opposite actually, right? And thus that means if you are able to maintain a balance between the output power from the generator and the load demand, then in that case you are able to maintain a condition of equilibrium between these forces, electromagnetic torque from the turbine, from the generator side, and the electrical torque from the load side, electrical torque. Now, instability, system may become unstable. This will occur, instability will occur if following the disturbance, you have a sustained imbalance. That means you continue to have some level of inequilibrium, imbalance between these forces, opposing forces. If you are able to have a sustained level, right, it's not just for one instant, but let's say time instant t1, time next, let's say after 2 seconds, after 3 seconds, after 4 seconds, or 5 seconds, or let's say 10 seconds, you are not able to achieve equilibrium, or you have sufficient level of imbalance, right, between those forces, then in that case instability may arise here. So that is the definition here. So now we say the ability of the power system to remain synchronous operation, it will be following some disturbance, as I said in the previous slide. So you are able to maintain equilibrium following the disturbance. And then what could be the disturbance? It could be severe transient disturbances, for example, here. Let's say the faults on the line, faults on the transmission line, or suddenly there is a fault on the transformer, or maybe the bus here, or maybe sudden outage of generator, or maybe sudden setting of load. So these could be some examples of disturbances. And because just say, it refers to the transient disturbance. That means you have a large amount of disturbance. Because if I say you have a trip of the line, let's say you have a line, and that line was meant to transfer a power of something 1000 MVA, right? And suddenly the line trips, fault takes place, and it's a permanent fault, and then line trips. So then what you observe? There is a sudden cut of 1000 MVA power transfer to the load center side. So thus a fault on the transmission line, and same way the fault on the transformer or the bus in the substation, that will result to a large disturbance, a large transient disturbance. Same way, even the loss of the generation, an outage of a large generator, 500 MV generator, 1000 MV generator. So this is a large loss, large amount of loss. Similarly, there could be examples saying that there is a 50% load trip. That could happen, but it is on very rare occasion. But if there is a sudden loss of a large amount of load, so that could be also as a transient disturbance. But normally what we experience, the changes in the load, they are by very small percentage. You may have, because load perturbation, load changes, it is random, basically what we observe here. It is basically as a stochastic, we define stochastic load perturbations, load variation. And in that case, we experience that our system, our network, it is always subjected to some random variation in the load. And we normally observe that what could be the variation in the load, if I say a random fashion? Any guess? Yeah, if I say random variation in the load, let's say from the morning hour till evening hour, what could be? Or maybe of 1 hour duration, what could be range? What could be the percentage variation? Any idea?
Maybe 5-10%.
Yeah, it will be in that 5%, 10% as a whole. But so over the 24 hour, if you say, we experience 5% or 10% variation in the load. But if you look into the monthly or the seasonal, there we can have a little bit large variation in the load here. In most of the cases, seasonal load variations, they are by much larger percentage here. So that could be also as a transient. But again, the seasonal variation of the load will not be as a transient. It will not be a sudden disturbance. It will not be as a sudden change, actually. Right. Then you should also understand that what are the factors which influence the stability, right? Because just see, if you have 1000 MVA generator, right, and you have 1000 amount of load, also 1000 MVA load. So your generator is at full rated value. Your load is at par with the load, the generation. Am I right? So the generator is fully loaded, right? Generator is fully loaded. That means generator is able to supply power at its maximum loading capability, right? Now, if in that case, if you experience a 20% increase in the load, what will be the impact on the generator?
It will slow down.
Yeah, because do you think the generator output power can be increased by 20%? Above the rated value, I mean, right? Above the full load condition, it will not be possible. You can overload the generator. That is possible by 5%, 10%. In some cases, it is possible. But if you have a large change in the load by 20% or 30%, and if your generator was already at full rated value, rated condition operating, then increase in the load cannot be met by your output from the generator. It cannot be met. So definitely in that situation, the system imbalance will take place. But if you have a situation where you have your power system or the power network where the generator is not fully loaded, let's say the generator is just loaded at 60% of its rated value, right? So if your generator is already in, because generator, as I said, your system initial condition, your initial operating condition could be at 10%, 20% loading condition, 30% loading condition, 40% or 100% loading condition. It could be any value. That's why it is said initial operating condition, right? So if I say your generator, it is just partly loaded. You have 500 MVA load on the generator, right? So if you have a 100 MVA increase in the load, and your generator will be sufficiently able to meet the increased amount of load. That is possible because the generator maximum loading is up to 1000 MVA, right? So depending upon the initial loading on the generator is only partly loaded. And if you have sudden increase in the load by 10%, 20%, or 30%, then in that case, generator output power can also be changed, and thereby you can have more power from the generator. So in that situation, the instability, the condition of inequilibrium will not arise. So thus it is very important that to understand what are the factors which influence the stability. So in fact, stability depends upon what is the initial operating condition here. All right. So that means your initial operating condition with the generator and the load was at rated value, full rated value, or it was generator was just 60% loading or 70% loading or 80% loading. And if in case you say that all the generators in a power plant, they are fully loaded, right? If you have all the generators in a power plant fully loaded, then if there is a load increase, then do you think the generator will be able to meet the demand? It may not be possible. And in that case, the stability will be affected here. So that's why we say the stability depends upon what is the initial operating condition, and then again, what is the amount of disturbance? What is the severeness in the disturbance level? Whether the change in the disturbance, change in the load, let's say the change in the load is just by 5% or 10%, and this change in the load take place over a period of 1 hour, 2 hour, or 3 hour, or 4 hour even, then in that case, it is very much possible to regulate the output power from the generator because you have sufficient time as well. You can regulate the output power from the generator in 1 hour, 2 hour, or like increase or decrease, you can do that. But if in case you have large change in the load and suddenly, let's say at t is equal to 0 plus, at this second, a 50% increase in the load is demanded, then your generators in the system, all the generators connected which you have it, they will not be able to meet the demand, sudden demand, all right, and there the condition of inequilibrium will arise, obviously. So thus the stability of the system will depend upon what is the initial operating point, and then about what is the amount of severeness in the disturbance here. Thus, one more point you should know, that post-disturbance steady state operating condition. That means if in case following the disturbance, your power network becomes stable, right? So that means your power system is able to achieve a state of equilibrium. It is able to achieve a steady state after disturbance, post-disturbance. So this operating condition, post-disturbance operating condition, will be different from before disturbance condition. So whatever the operating condition which was before the disturbance and the condition which is after the disturbance, it will be always different. It will be always be different here. So here, this slide again with the common term.
Hello, Prof.
Yes.
I want to ask concerning the stability of the power system. We talk the stability.
Yeah.
Okay. If you have a power system that has maybe rated, let's say 500 kVA, and the load demand is about half 50%.
Okay.
So in a situation like that, does it need automatic regulator to achieve stability, or what do you need to do?
Just see, if you have a situation in the power network, in the power grid, where you find that generation is more, but the demand is less, right? Okay. If
Yes.
your power grid, let's say that if I take your example, Nordic grid, and if I assume that your demand is less and generation is more, right? So in that situation, the system is not very much stress, because the system operator they know that they are capable to generate more power on the demand. All right, because your demand is less, but since they have sufficient generation available and the generators remain connected to the network, and if you have more generation capable in the system but the demand is less, then the system is not stressed. So in that situation, just remember one thing: electricity cannot be stored in bulk amount. All right, it's not a small amount. I saying 500 MVA, 500 megawatt, or 1000 megawatt, or say 5000 megawatt something. So we don't store such huge amount of energy actually in the battery and also, right? So we have to meet our demand instantaneously, right? And in that situation, your system operator or the power plant operators or the transmission network operators, they will always regulate their generators as per the demand. If the demand changes, if the demand increases, they will regulate more output power from the generator. Right? So this is automatically done. This is automatically done actually, because normally we follow what is the change in the load, what is the change in the frequency, and then we have the use of the governors, and then they do the governors will regulate the output power from the generator. We do it automatically. We do that. But if you have a situation in the system where demand is more and the generators which you have connected in the network, they are not capable to meet the demand, then what you will do? Am I right? There, the system instability problem, it is much more severe. It will be much more severe because you do not know, because you don't have any control on the load. All right, just see the plant operators or the transmission network operators or the distribution network operator. In fact, the transmission operators and your plant operators, they can regulate their generators. They regulate their generators, but they normally do not regulate their load actually, the connected load, right? And you don't control your load, and it is all based on the consumer demand. And sometimes the load demand is more or less, but if it is more, you don't have any control on the demand, then in that case the generation cannot be met here. The whatever the generators you have, their output power cannot be regulated to meet the demand. Then what you will do? There the system instability, it is much more severe in terms of consequence, I can say. Is it okay? Was it answerable?
Yes, it's very okay. Thank you.
But we do. But your point was saying that can it be automatically, right?
Yes.
Yeah.
You said yes.
We can. Yes, we can do that automatically. We always we have the automatic regulation of voltage at the bus. We have the automatic voltage regulation at the bus. We also have the frequency. We do it automatically. But again, let me tell you, this automatic regulation we talk about, it can be as a small level, a small power network level, right? But if you have a large, big network, geographically spread network, right? And then if you have one centralized control center, I mean, which will be required to maintain the regulation of all the, let's say, thousands of generators, and you have several amounts of load and thousands of lines, thousands of generators, there it is little bit difficult or complex in terms of regulating the generators. Yeah, there it is little bit different. For a small size, small network, for there it is okay if you can do that. But for a large network, it becomes little bit much more complex, and that's why monitoring is required, very much necessary in that situation. Right? Okay. So we move further. So here we have this slide to discuss what are the disturbances in the power system. And in fact, these disturbances, they could be as a sudden change, or it could be as a sequence of changes, right? And that could result into variation in one or more parameters. So that means because of the disturbances, it could either a sudden disturbance or a sequence of disturbance that will result into change in the operating condition. That means change in the deviation of the system variables. And thus, this deviation in the system variables will depend upon what is the amount of disturbance that takes place, whether it is sudden disturbance or a sequence of disturbance, right? So thus we have a small disturbance, or we have defined it large disturbance. Now this, the quantitative term which we have it a small or the large, it is actually referred to the amount of disturbance for which the system dynamic behavior can be linearized for analysis. Let's say the system is initially at a steady state, right? And it is equilibrium, it is a steady state system, right? No perturbation. But if I say that there is a small amount of change, let's say 1%, 2%, 3%, 4%, or 5%. Let's say your generator was 500 MVA, your load was also something 500 demand. So this is a perfect match. All right, steady state operating condition, perfect equilibrium. Now let us assume that there is a change in the load by 10 MVA. Now 10 MVA, it is initial operating condition was 500 MVA, right? Now 10 MVA, if you take the percentage out of 500 MVA, it is how much percentage? It is very small percentage, right? So if there is a small disturbance, let's say by 1%, 2%, 3%, 4%, or up to a maximum 5%, then in that case, the system behavior, the system dynamics behavior can be linearized. Yeah. So that means if the load has increased by 10 MVA, your generation will also increase by 10 MVA. So that means it is 510 MVA now, right? So thus the system dynamic behavior for this much change of 10 MVA, it is very small change, and the system operating condition change will be very small, and thus the system behavior can be linearized for analysis purpose. But if you have a large disturbance, let's say your generator was 500 MVA, your load was 500, initial operating condition, steady state. But suddenly you have a load increase of 400 MVA, right? It's a initial point operating point 500 MVA, but suddenly there is a load increase of 400. So that means now you want total generation output to be 900 MVA. So that means initial operating condition was 500, and now your change operating condition should be 400 more. It should be 900 MVA. So thus the change in the operating condition from 500 MVA to 900 MVA, it is much larger. And thus mostly the system which we have, it is a non-linear. And for such large disturbances, the system equations which describes the dynamic behavior of the network, they cannot be linearized. We need to have a non-linear behavior, and we need to have, because in that case it will be a system dynamic behavior will be a non-linear, and thus we need to have use of non-linear equations for large disturbance change for analysis purpose, and thus those will be under the category. So thus those disturbances for which those disturbances for which the system dynamic behavior cannot be linearized for the analysis. So those disturbances, we call it as large disturbances here. So this is, so normally we observe that all the disturbances which are above 5%, for their case, we always use a non-linear model. We don't use a linear model. And if the disturbance is up to 5%, then in that case, the system can be linearized, and we use a linear model here, right? So this is next, we have the term steady state stability of power system. Earlier, we have defined the stability. So we have now, that means based on the disturbance, based on small disturbance or the large disturbances, we have these two terms, steady state stability or transient stability. So steady state stability will refer to the ability for the system to remain stable following a small disturbances and reaching a steady state operating point, which will be very much similar or very close to the initial or the pre-disturbance operating condition. So if you have a small disturbance, then in that case, the operating change in the operating condition will also be small, right? And the system will reach to the steady state, right? It will reach to the steady state if there is a small disturbance. And this we call it as a small disturbance stability here. So the small disturbance stability is for small disturbances only. And in that case, we assume that the system is able to achieve a steady state operating condition. That means there is no deviation in the system variables here. System is that steady state, right? However, if there is a large disturbance, then in that case, here we define transient stability. So it will be, again, we assume that the system is also remain stable again large disturbances. So we say that ability of the system to achieve synchronism, that means to achieve stability, to maintain stability. Ability of the system to maintain stability following a large disturbances, following a severe disturbances like fault or change in the loss of generation or loss of load here. Because of a large disturbances, then you have large deviation in the frequency, you may have large deviation in the angle, a large change in the amount of the power flow in the line, the bus voltage, and other system variables. So if the system is able to maintain the synchronism following a severe disturbances, then we say transient stability. So again, it is an ability, but against severe disturbances here. Right, so that is the difference between the steady state stability and the transient stability here, right? Anything?
Hello, Prof. Maybe before someone asks question, can we have a short break after anybody has asked question?
Yes. Okay, fine. Agreed, fine, agreed, okay. Maybe I would, right. Okay. So any query that you have on this slide? Yes, please. No. Okay, then. So here I have this slide to explain a little bit more what could happen if the system becomes unstable. So that is consequence. So if you have if the system becomes unstable, you may have a runaway situation or a rundown situation here. These two are different depending upon the variables they are associated to. So for example, if we have a progressive increase in the angular suppression between the generator rotor, it will be as a runaway. Right? Increase in the angular suppression. If you remember earlier, we have said the relative motion of one generator with respect to the network or with respect to another generator. So that means the angular suppression, the relative motion, if the angle difference between one generator deviates out, it increases, progressively increases with respect to the system network, or it may be the another generator. So that means there is an increase here. So that it will be a runaway situation here. Then another one is rundown situation, a progressive decrease in the bus voltage. So that means, let's say slowly, you have a drop in the voltage. This will be a rundown situation, and it is something like this, yeah. Right? So here we have to find here that the speed or the frequency. Yeah? We have the blue line and we have the red line. And we want that our system frequencies should be 50 Hertz here. If the system is stable, remains stable, following the disturbance at this instant of time, then the frequency will have some deviation, it will have some oscillation, but you find here that the disturbance took place here, and since the disturbance was of a small magnitude, let's say, so there will be some oscillation, some deviation in the frequency you will observe, but after 15 seconds, the frequency is restored back to 50 Hertz here. So that means you are able to achieve a perfect 50 Hertz signal here, 50 Hertz frequency here. You are able to maintain the system stability. But let's imagine that you have some amount of disturbance, large disturbance, for which the frequency progressively increases, goes beyond 50 Hertz, it increases to 55 Hertz here. All right. Can you tell me why this could occur? Let's say you will have increase in the frequency when this can take place. You have the generator feeding power to the load. When you will observe increase in the frequency?
When the supply is much more than the demand.
Yeah.
Yeah. So, but when this could take place, this increase in the frequency?
It could be as a sudden shutdown in the load demand or sudden change in load demand.
If in case, let's say there is a sudden load change and suddenly the load has reduced by large magnitude. If at t instant to t is equal to 0 plus here, at t is equal to 0 plus here, you find that the load has suddenly reduced to 0. Now in that case, just see, the generator cannot be shut down instantaneously. Generator has inertia, whether you have thermal power, steam generator or hydro generator, they will be still running. Suddenly the load is cut. Let's say you have the switching operation for the load, and at t is equal to 0 plus, with the switching operation, suddenly a large amount of load is cut. But the generator cannot be stopped suddenly. Generator has inertia and it will continue to rotate. And because of that, the system frequency will increase here. So this is just an example showing that the system is now getting unstable. Now in this case, the frequency increases beyond the limits here. Then in that case, you will have over frequency relay. You will have over frequency relay operation on the generator, which will trip the generator and which will, that means, shut down the generator now. So if this over frequency is measured, it is sensed by relay, then in that case, the relay will operate, over frequency relay will operate, and it will shut down the generator. Similarly, even when the frequency drops, then we have under frequency relay, and it will trip the generator. So because we want to protect the generator, so we have the use of over frequency and under frequency relay for such situations that may arise. Now, so this will be the case of instability here. Next, I just want to give some real examples here. So in this case, you observe that, as I said, runaway situation. So you have the increase in the angular angle here between the generator rotors here, or it could be generator rotors, or it will be the bus angle basically. What you find here that the fault because of the disturbance that took place, the bus voltage of Kemau, this is here, and the bus voltage of Sundance. Now what you find here that the bus voltage of Sundance, it is deviating out. It is going out of step. There is a progressive increase here in the angle, the bus angle of Sundance with respect to the Kemau here. So this is actually a runaway situation, a progressive increase in the bus angle between the two here. So this is actually the example where we observe the increase in the rotor angle of British Columbia and Alberta here, where we have the blackout occurrence. So we find that the deviation in the rotor angle or the bus angle of Sundance deviating out with respect to the Kemau. So this is the runaway situation. Similarly, if you refer to the rundown situation this way, so what you find here that the bus voltage, which is about 550 kV here, right? The steady state value at 0 time, it is 550 kV here. We find that there is some disturbance taking place, and there is some deviation in the bus voltage here, right? But we find that around this time instant, after this actually, from 23 seconds onwards up to 30 seconds onwards, within 7 seconds here, within 7 seconds, what you find that the bus voltage drops suddenly. There is a sudden drop in the bus voltage from 550 kV to 300 kV here. So within 7 seconds, the bus drops here, the bus voltage drops here. So this is actually a progressive drop in the bus voltage here. And that was the case, and this which we observed in the case of Western Northern America interconnected system blackout here. So these are some of the real examples where we have the instability because of these situations here, runaway and rundown situations here. This I have this is, we call it as rotor angle instability, and this we call it as voltage instability. And I have referred this from the lecture by P.S. Kundor here. Then again, there have been several series of blackouts.
Hello, Prof.
Yes, yes.
Please, if we go back again to that same previous slide, this slide. Yeah. Now, you make mention of relays that are used in sensing the difference in the instability. I want to ask, is there a specific number of seconds? Take, for instance, some disturbances could just be transient and it will restore back to its stable state. Does you have a specific number of seconds that relay has to track before it trips up in order to protect the generators or the equipment?
I think your point of question is that do we have some delay in the relay operation? Do you want to know this?
I'm talking of the configuration of the delay of the relay. Are they just designed in such a way that once it sends, it trips up, or once it sends, it observes it for 30 seconds before reacting?
Okay. No, in my understanding, just say in the design of relay, okay, there could be some delay introduced, right? There could be some delay that I can say. But normally, if what I know about the over frequency relay or under frequency relay, right? Now, the operation of over frequency relay and under frequency relay, it is all based on what is the change in the frequency there. That means the deviation. Let's say that you want to have an allowable limit of 2% frequency deviation in the system, for which the system remains synchronism. For which the system remains synchronism. So if you have 2% change here from 50 Hertz, either plus side or minus side, so whenever this change, 2% change crosses the limit, then the relay will detect it. All right, it will detect it, because remember one thing, it is possible that the change in the frequency, if I say, for example, at this instant, the disturbance takes place, but there is a continuous disturbance taking place, right? And you are not able to have the regulation on the generator. Let's assume that way. So frequency will increase here. Frequency will increase here. And let's say that this is your limit. This is your limit. And at this instant, you find that the frequency deviation crosses the upper limit. And then at this instant, the relay will trip the generator. That will take place.
Okay, thank you.
That will take place. Similarly, it happens with the under frequency relay. So let's say you have an lower limit defined, and let's say the frequency dips, and you are not able to regulate your generator, and there is a continuous dip, and then at this instant, the frequency deviation reaches the or crosses the lower limit. Then again, under frequency relay will operate here. It will operate here. But you talked about the time, right? In your question, yeah.
Yes.
What do you mean by time actually? Time of operation of the relay or the regulation of generator? What does this mean actually?
Okay, I'm trying to talk about the time of the relay operation. You know, some disturbances could be very high and very transient.
Okay.
Just be microseconds.
Right. Okay.
So a situation like that, whether
okay. Now just see. Normally, we don't have any delay, because even the relays, they operate in milliseconds. The relays, they operate in milliseconds. So, but the deviation in the frequency, I mean, the profile of frequency change, it all depends upon how does the governor will respond basically, and what is the amount of load disturbance. If there is a sudden load disturbance, so definitely it is possible that the governor is not sufficiently able to regulate the output power from the generator, right? Because the governor itself has a delay. And then in that case, the frequency suddenly it can cross the upper limit. It can happen. And then in that case, the relay will instantaneously trip here. That is possible. So that means in this case, you find that relay will trip in 2 seconds or less. But in this case, you find that the relay will trip in after 4 or 5 seconds. So it depends upon how does the profile of the frequency changes. It depends on that. And when it crosses the limits, upper limits or the lower limits actually. But nothing to do that saying that, okay, it is at this instant of time, the disturbance takes place, and then after that much time, the relay will operate. No, it is not that way. It is based on sensing the frequency deviation. It is based on that. Right?
Okay, thank you.
Right. So maybe I will have one more slide, and then before. So I just have this example to mention here, that we have a series of blackouts occurrence worldwide, and I have listed some of them mainly in the Europe. So if you refer to in 2003, it was August 14. In fact, that was in the northeast of USA, Ontario. This much amount of load being affected, this many people. And then in the same year, that was in the Europe. So it was 23rd September in the region of southern Sweden and eastern Denmark. 6,500 megawatt of load loss. And then after 5 days, it was in the bigger continent level, the blackout in Italy. And here it was 50,000 megawatt load change disturbance. And then another in the following year in 2004, it was in the Australian region where we had something 1,000 megawatt. So we had several series of the blackouts. I have just listed very few of them, but even in the American continent and even in the Asian, in fact, even in the Indian system, there was a blackout in 2012. So we had, and again, if you come across, if you have heard of, do you know that in the Ukraine there was a blackout recently, 1 year back or 1.5 years back? Have you heard? Yeah. The complete power shutdown, the generator outage in the Ukraine region. Do you know? Anybody has the news? No.
No.
Yeah, recently there was a blackout in the Ukraine about 1.5 or 2 years back. And let me tell you, it was not actually system disturbance, right? Either the load change or the generator change, right? It was basically a cyber attack. So some people, or you can say, through the communicate, because your power network, it is now all interconnected through the communication network, actually, right? And some people had intruded through the communication network, and they had manipulated the valve. They had manipulated the valve position of the steam turbine. So that means if you manipulate, that means if you change the position of the valve of the steam turbine, and it was all done remotely through the communication network, they have changed the setting of the valve through the governor and in the steam turbine. All right, it was done remotely. There was nobody in the power plant who did this actually. All the settings were manipulated remotely, and it was all the setting was modified through the communication network. Because the system is all power network connected actually, and they manipulated, and as a result, the generator started behaving abnormal way, right? And thus the relay had operated the generator to shut down, and thus some of the generators in the system, they were shut down, and it was not because of some problem. But it was a intentional problem introduced to the cyber attack in the system, leading to the blackout. That is what, if you can read some news about it, about the Ukraine blackout. So this is what they say about the cyber attack in the power plant.